with traditional FRTS, class-based shaping allows us to shape just the necessary traffic. Now we will apply this policy to S00. The same policy could also be applied to the sub-interface. We've applied our policy outbound interface 0. Now let's take a look at how this policy is operating. We'll use the show policy interface command. Here you see the 30-second offered rate of 50,000 bits per second for the aggregate. The drop rate is 0 at this particular time. Note also our CIR, committed burst, and our interval of 125 milliseconds. Every 1/8 of a second, the shaper will send 1,000 bytes to the interface in order to achieve our shaped rate. You also see the current queue depth of 6, and the shaping is therefore shown as active. Suppose we wanted to shape traffic at the PVC level rather than at the interface level. Here is an example, again working from the bottom up. When you want to apply parameters to individual PVCs, you must put these parameters in a map class frame relay, like the one you see here. You see that we have used the service policy command within the map class to apply a policy called shape default outbound. Here is the shape default policy. Note that our shape average command has been applied to the class default. This is the only class that can be shaped when the policy is applied directly to a PVC. This does not mean, however, that you lose control of what traffic gets shaped. In this situation, we can control the traffic that gets shaped by controlling which traffic falls into the class default. Class default is the final catch-all class that contains all traffic not previously matched in the policy map. We want to shape only traffic that does match class 26016. We can get this traffic by itself in class default by creating a class that matches everything but this traffic. This is the power of the match not command in the class map syntax. All traffic other than the targeted traffic will match our class not 26016. This will leave only the traffic that does have destination port 6016 in class default. This logic may seem a little tortured, but it is in fact widely used. Now that we have all the traffic destined to port 6016 in class default, we want to segregate it by source port and reserve bandwidth for traffic sourced from port 6012. This is the stream that is sent at the steady rate of 40K. In order to manage the shaping queue, we do a hierarchical policy. The shaping policy is created by the parent policy. In our case, the parent policy is called shape 6016. The child policy is applied to the shaping queue using the service policy command. In our case, it is called reserve, and it guarantees 45K of bandwidth for class from 6012. Note that the service policy command that applies the child policy does not have a direction. The direction is inherited from the parent policy. Also note that the sum of any bandwidth reservations in the child policy cannot exceed the size of the shaping queue. If we wanted to enter our bandwidth reservation as a percentage, it would be a percentage of the parent bandwidth. In the reserve policy, we could have used the command bandwidth %70 and gotten the same result. Now let's see how this policy works. We will remove our old policy from S00 and apply our map class to del C102. Now that the policy is applied, we'll enter our show command. You see that the output is broken down by PVC. First, we see the performance of our parent policy, Shape 6016. We have had no hits against our Not to 6016 policy. This is a very tightly controlled lab environment, and we have turned off all control traffic, including LMI and routing protocols. Note that class default has averaged 55,000 bits per second over the last 30 seconds. This is our traffic destined port 6016 that didn't match above. You then see the shaping parameters applied to these flows. Note our CIR of 64,000, committed access rate. Here you see our sustained bits per interval, which is our committed burst, and our interval of 125 milliseconds, or 1/8 of a second. Next, you see the data for our child policy called reserve. Remember, this policy sets aside 45K of bandwidth for traffic in the shaping queue with source port 6012. This traffic is leaving R1 at the same rate it arrived, which is 40K. We're very close to it at 39 kilobits per second. Class default in the reserve policy contains traffic with the other source port 6011. This is the traffic that varies, and at this moment it's about 18,000 bits per second over the previous 30 seconds. Since we have reserved bandwidth in the shaping queue for the traffic from source port 6012, it will not be dropped. Instead, the queue will drop the variable traffic from source port 6011. Let's go over to R2, where we have applied our count policy. This is traffic captured earlier when the pipe was completely full. You note we have 24 kilobits of traffic in the variable class and our full 40,000 bits per second for the traffic from 6012. If we could check these counts on R1 at the same time, we would likely see that the 6011 rate is really above 24K. The excess is getting queued and dropped if necessary on R1. We should always get the full 40K rate of traffic with UDP source 6012. Class-based shaping can seem complex when you get into hierarchical policies applied at the PVC level. But the payoff for this complexity is power and flexibility. If you run data across frame relay PVCs, you'll probably need to shape it. Class-based shaping on Cisco IOS provides an excellent tool. In order to achieve good voice quality over frame relay, we must minimize delay and jitter. To accomplish this goal on low-speed links, we need to implement priority queuing and advanced link efficiency mechanisms. In this presentation, we will examine how the AutoQoS Voice over IP macro implements these goals. Many books have been written on the topic of supporting Voice over IP on Cisco routers. It is a complex topic. Starting in the 12.2T train of iOS, Cisco introduced the AutoQoS Voice over IP macro to ease the deployment of Voice over IP on its routers. By issuing one command, the recommended class maps, policy maps, shaping, and compression commands can be entered for us. Examining these resulting configurations can tell us a lot about how to implement Voice over IP over frame relay. There are two versions of this macro. When you issue the command with the trust keyword, iOS assumes that traffic is already properly marked as voice media or voice signaling packets. When the command is issued without the trust keyword, iOS uses a combination of NBAR and known common protocols and port numbers to identify and mark the traffic. AutoQoS Voice over IP can be applied only on point-to-point links. These can be serial interfaces encapsulated HDLC or PPP, or they can be ATM or frame relay PVCs on point-to-point subinterfaces. The macro uses the interface bandwidth to calculate shaping parameters, so we need to make sure it is set properly. Our example sets the bandwidth to 256K, which is equal to the CIR of the PVC. Let's go ahead and set the bandwidths on our subinterface. After making sure that the bandwidth is properly set, we go into configuration mode for Del-C 102 and enter the command AutoQoS Voice over IP with the trust keyword. After a second or two, it reports the creation of a class map. In fact, the macro has made a number of changes that we will review. Let's take a look at the changes that it made at the interface level. We'll take a look at some of these changes in detail. Note that the macro enabled traditional frame relay traffic shaping on the physical interface. This is not enabled in order to buffer and smooth traffic flows. Instead, frame relay traffic shaping is required in order to permit per Del-C queue management and FRF12 fragmentation and interleaving. On the sub-interface, you see the bandwidth statement entered earlier. Under Del-C 102, you also see the macro command. The macro has created and applied a map class frame relay. It contains the per Del-C traffic shaping parameters. We'll examine it in the next slide. Finally, under the interface, you see the RTP header compression has been enabled. Voice over IP packets often consist of a 40-byte header with just 20 bytes of data. This header information consists of the 20-byte IP header, an 8-byte UDP header, and a 12-byte RTP header. By enabling RTP header compression on the interface, this header information can be squeezed down to just 4 bytes of information. The entire voice over IP packet is then just 24 bytes rather than 60 bytes, saving 60% of the bandwidth. The map class frame relay has been automatically named for the interface and the Del-C where it was applied. Note that the CIR is set to the configured bandwidth. The committed burst is set to 1% of the CIR. This has the effect of setting the shaping interval to 10 milliseconds, or 1/100th of a second. An interval of 10 milliseconds is often used for voice over IP. One of the primary goals for this macro is to minimize the delay for voice packets. When the total end-to-end one-way delay for voice packets is much over 150 milliseconds, voice quality noticeably suffers. In order to stay within this budget, we want the delay for one interface in the path to be under 10 or 20 milliseconds. By default, frame relay sends packets to the interface for transmission every 125 milliseconds. If voice packets had to wait that long, most of the end-to-end delay budget would be spent. By lowering the interval to 10 milliseconds, this frame relay interface adds much less delay. To get an interval of 1/100th of a second, we set the committed burst equal to 1/100th of the CIR. In order to protect voice quality, the macro sets the excess burst value to 0 and the minimum CIR to 256K, equal to the CIR. In combination, this means that we will not burst above the CIR or throttle below it. Allowing bursts above CIR would expose our voice packets to the potential of being dropped by the provider. Min-CIR is the maximum reservable bandwidth for the shaping queue. By default, it is equal to 1/2 CIR. The macro sets it to the full CIR because it will apply a policy that reserves bandwidth for the voice packets. We will examine this policy, called AutoQoS Policy Trust, in a few minutes. Here you see it applied in the map class using the service policy command.